Here's the fourth video of these review videos, and it covers solving exponential and logarithmic equations. And I should say that in solving any of these equations, if you are absolutely certain your solution is correct, you can skip verification if you want. In other words, there's no points or bonus points for checking solutions, only deductions for incorrect answers. Now, if you do want to check any solutions to any of these equations, be sure to substitute them into the original equation. And we will see how important that is with our first example. Now these follow in the same order as they were presented in class and as they appear on the PowerPoint, which, if you read the announcement, is available. You'll see that it is available on the Canvas website. So in this first one, we have two logarithms here. We combine them using the power property of logarithms. We combine them into one. Then we convert this logarithmic equation into an exponential equation by using 3 as the base and putting this side of the equation into the exponent, and we take this argument, that's whatever's inside the parentheses of your logarithm, and putting it on the right side of the equation. That's the exponential equivalent. And from there, 3 cubed is 27, and it's a quadratic. The best way to solve a quadratic is to set it equal to 0 and factor, which is what we've done here. And we have two possible solutions then, 3 and -9. If you put -9 into the original equation, then of course you'll be taking log base 3 of -9, and you can't take the logarithm of a negative number. If, of course, you substituted them into one of these equations, you would get equality. So that would fool you into thinking that was a correct solution. That is why you must always put, for verification, you must always put your possible solution into the original equation. Now for the next one, for the next equation, we combine the two logarithms on the right side into a single logarithm using the product property, and then multiply x plus 3 times x plus 4, you get x squared plus 7x plus 12. And then you have the same, a logarithm with the same base on each side. That means you can drop these logs off and just set the arguments, 5 minus x and x squared plus 7x plus 12, equal to one another. And once again, you have a quadratic. Add and subtract everything as necessary to and from both sides of this equation to set everything equal to 0, factor, and come up with your possible solutions, -7 and -1. And here we have two possible negative solutions. The reason that we can do this is that if you take the logarithm of -1 here, -1 plus 3 gives you 2. Actually, you're not taking the logarithm of -1. If you're substituting it back into this equation, so -1 plus 3 is positive 2, -1 plus 4 is positive 3. So you can take logarithms here of positive numbers, and if you substitute -1 here, this will be 5 minus a -1, which is the same thing as 5 plus 1, so you're taking the logarithm of a positive number here. And if you finish all the calculations, you'll see that you do get equality. Now, in both of these equations here, you're writing both sides of these exponential equations with the same base. In order to do it in this first equation, you apply the product property and the product to a power property that's found on the properties of exponents and radicals side of the one-page handout that I distributed in class. I also have placed a PDF of that document in the files section of our Canvas website, And so if you lost your copy, or if you'd just like to have a PDF, it's there for you in the files section. And so using those properties here, we wind up with 2 to the negative 3x and 2 to the 3x minus 6. If it is unclear how we arrive there, you might want to go to the tutoring lab and have one of them explain it, or you can text or call me at 210-464-5781, and I can go through it. And you have a linear equation that solves as x equals 1. And again, if you place that 1 back in the original equation, you will get equality. The next one is pretty straightforward. You wind up with a simple quadratic. Both of these values solve the equation if you want to substitute them in and check that out. Now, the next equation uses we can't write both sides of this equation with the same base, so we take the logarithm of both sides. And in class, we saw that whether we take the natural logarithm or the common logarithm, we will get equality, and or rather we will be able to apply the power property. So once you take the logarithm of both sides, the power property, again from that sheet that I gave you, says that we can take this exponent and bring it around front, and this exponent and take it around front, and don't forget that this entire expression is the exponent, so we can take that around front, and we distribute the 3x minus 1, and that gives us 3x times the natural log of 2 minus natural log of 2. We add and subtract as necessary to isolate the terms that have an x on one side of the equation and those that don't on the other. Factor an x out, and then divide by this number here on both sides to get your solution. Putting this back into the original equation to solve might not necessarily be as easy as in the other equations, but you can do it if you want, if you have a calculator and you know how to use it to do this. I would probably just check my work to make sure that I had it right, as opposed to trying to check the answer in the calculator, because you're just as likely to make a data entry error on your calculator as anything else. Also, when you get to an answer like this, leave it. It's just fine. There are ways to simplify this, but just this is the best answer for me, just leaving it like this. Now, the last of these equations is going to involve a u substitution, or if you want to use v or w or whatever, but you're going to substitute, and you're once again going to apply the product to a power property and the product property to substitute 3 to the x for u. And when you see that this has a base of 3 and this has a base of 9, which is a power of 3, then that should tell you that you want to use 3 to the x. Could be 4 to the x, could be 2 to the x, you never know. But that tells us that we're probably going to use 3 to the x, and we apply these properties so that we substitute u for 3 to the x. Once again, if this is something that is really challenging to you, the tutoring lab, that's JH316, has plenty of tutors who can help you out with that. So I substitute u in for the 3 to the x, so that's u squared plus 3u minus 18, and again, it's quadratic factors. Your solutions are u equal 3 and u equal negative 3, rather negative 6, but we are not finished. We're not finished. You have to substitute 3 to the x back in for u to check what you're, and to finish, to conclude, and so we see that 3 to the x is equal to 3. It should be pretty obvious then that x is equal to 1. And in this case, 3 to the x is equal to negative 6. that means that that is not going to give us a solution to the equation, because there is no value you can raise a base to. There's no exponent that will give you a negative number. And one last set of questions involve exponential decay, radiometric dating using exponential decay. And in those, so we have the two stories here, you can read about them, and we are given the numbers that we need to calculate. In each case, we are going to calculate the decay factor. And so the half-life means, or the half-life of potassium-40 in the first case means that we set 1/2 equal to E raised to that time, that amount of time, which, as it says here, is 1,251,000,000 years. And you take the logarithm of both sides, use the natural logarithm so that you can cancel the E out here, and divide by that 1,251,000,000 to get a decay factor of negative 0.0000000000054, which I think is 5.54 times 10 to the negative 10th, I think. But it's probably going to be just as convenient to use the decimal version of that. And when you substitute that into the equation using 89.76 in decimal form, 0.8976, then you'll come up with 195,001,343.346 years. Can't really be that accurate. Probably 195 million would have been just as good an answer. And then a similar procedure is performed over here, and you can follow comparing the numbers with the equations here and the solutions here, and you'll see that we end up with another very old sample, 231,630,551. How far you round is probably not the thing that's going to get you in trouble on these questions. So, a reasonable approximation, especially if you have this work to show me that you knew what you were doing, is good enough. There's my number in case you want to text me or call and leave a message if you have any questions.